Hello, Chem 1. In 4.1, we talked about light, energy, and the electromagnetic spectrum, and how light and energy interact with electrons around an atom and help us understand how those electrons are arranged. Today, we're going to talk more about how those electrons are arranged in something called electron configurations. Electron configurations are a model that help us understand how electrons are arranged. This comes from the study of quantum mechanics. In quantum mechanics, we use something called quantum numbers. They are variables that help us identify where electrons are located. You need to think about quantum numbers as an address. We start out very zoomed out, and then as we get more and more quantum numbers or more and more variables, they help us kind of home in to where that electron is located. So if you look here, we see 4 quantum numbers, N, L, M, S. Those are the letters that are the variables for those numbers. The analogy we can use is a hospital complex. So for instance, the most zoomed out level might be the building level. That would be N. And then as we zoom in what floor of the building are we on, and then what room on that floor, and then what bed in that room. So with the 4 quantum numbers, we get an address for that electron. This quantum mechanical model comes from research done in the early 1900s. Some of these people you've probably heard of before. One of them is Heisenberg, and he developed something called the Heisenberg uncertainty principle. What Heisenberg discovered was that because electrons are very small, moving very fast, anything you did to try to observe them would actually manipulate the path of the electron, and therefore you could not observe it accurately. Therefore, the position and the speed of the electron is uncertain. Heisenberg's uncertainty principle. So based on that research, Schrödinger comes in and develops equations. And he says, I might not know exactly where these electrons are, but these equations can give me probable locations of where the electrons could possibly be. And this brings forth the idea of the atomic orbital or the atomic cloud. This is where we get the atomic cloud model. It's not based on these defined rings of energy like Bohr said. It's more probable locations based on the math from Schrödinger. And every atomic orbital can only hold 2 electrons, or every room in the hospital only has room for 2 electrons. So let's walk through these quantum numbers. The first and most generic quantum number is the principal quantum number, or the principal energy level. These numbers are 1, 2, 3, 4, 5, 6, 7, because there's only 7 energy levels around any atom. These numbers correspond to Bohr models and how many energy levels, or how far away from the nucleus those electrons are. So the first 2 electrons always get put in the first energy level closest to the nucleus. Within those energy levels, those principal energy levels, we have sublevels. There are 4 sublevels, and they are S, P, D, and F. So if you wanted to tell the energy level and sublevel of any electron, you could say this is in 1s, energy level 1, sublevel S. Or you could say this is in 3D, and energy level 3 and sublevel D. In each sublevel, there's a given amount of orbitals or rooms. Remember, atomic orbitals can hold 2 electrons. They each have a positive spin or a negative spin. But different size sublevels have different numbers of rooms. So an S sublevel only has 1 room, and therefore can hold 2 electrons, because every room can hold 2 electrons. A P sublevel can hold 3 orbitals, which means it can hold 6 electrons. A D sublevel can hold 5 orbitals and therefore has 10 electrons that it can place. And then F can hold 7 orbitals and therefore 14 electrons could be placed in an F sublevel. Just as I said a little earlier, the reason that you can put 2 electrons in those orbitals is because one has a positive spin and one has a negative spin. And a lot of times they'll be represented by an up arrow and a down arrow to kind of differentiate between the 2. If you look here in this chart that's in your notes, you can see the type of sublevel. We have S, P, D, and F, and then it tells you how many orbitals or how many rooms are in each of those sublevels, 1, 3, 5, and 7. And then you can see what those orbitals are modeled like based on Schrödinger's equations. Remember, these orbitals, their shapes are based on Schrödinger's math. Okay, if you graph those equations out, these are the shapes that they take on. You'll also notice these sublevels in which energy levels they're located in. So if you see, an S sublevel is in all 7 principal energy levels. A P sublevel is in all principal energy levels except for 1. D is in every one except for 1 and 2. And F is in every one except for 1, 2, and 3. So what's that mean? It means that the first energy level only has 1 sublevel, S. And it means that the second energy level has 2 sublevels, S and P. And the third energy level only has 3 sublevels, S, P, and D. And finally, the fourth energy level has all sublevels. And now we can fill out the last row of the chart. S sublevels have 1 orbital, which will hold 2 electrons. P sublevels will have 3 orbitals, 1, 2, 3 shapes, and therefore can hold 6. D sublevels can hold 5 orbitals, 1, 2, 3, 4, 5, 2 in each gives us 10. And then F sublevels have 7 orbitals, which means they can hold 14 electrons. This is another chart in which it's arranged by energy level. You can see over the side we have our 7 energy levels, and we also have the number of sublevels. The first energy level only has 1 sublevel, S. Second has S and P, SPD, SPDF. Just so you know, G, H, and I, those are sublevels that Schrodinger's equations showed, but they're theoretical. We don't need to fill them because we don't have enough elements to house that many electrons. You can see here over to the right, this would be the total number of orbitals in this energy level. So there is 1 energy level here and 1 orbital in that energy level, which means the first energy level can only hold 2 electrons. But in the second energy level, we have 2s and 2p. S would have 1 orbital, and p sublevels have 3 orbitals for a total of 4 orbitals, meaning the whole second energy level can hold 8. If you remember from physical science, when you drew atomic models, you always put 2 electrons in the first energy level. It's because of 1s. And in the second energy level, you put 8. Why? Because of 2s and 2p together can hold 8 electrons. In the third energy level, we have 3s, 3p, and 3d, which is a total of 9 rooms because s sublevels hold 1 orbital, p's hold 3, and d's can hold 5. So the total is 9 orbitals, which means a total of 18 electrons can be placed. And we can keep on going all the way down to energy level 7. Now that we have a decent understanding of those electrons and how they're placed in those rooms, let's start actually placing them in something called an electron configuration. There are 3 rules to know here. The first one is the Pauli exclusion principle, which says no 2 electrons can have the same 4 quantum numbers. If you were using the hospital analogy, no 2 patients can share the same bed. Everybody needs their own address. The off-ball principle says that electrons are going to fill the lowest energy levels first, meaning we're always going to start with 1s. It's the lowest energy, it's the closest to the nucleus. We'll fill that energy level first, then we'll move on to 2, and then we'll move on to 3, and so on. And then finally we have something called Hund's rule. Hund's rule states that when we're filling a sublevel, we have to give every room a patient, every room an electron, every orbital an electron, before any orbital gets 2. What does that look like? So let's say we're looking at 2p, the sublevel. Remember, p sublevels have 3 orbitals, 1, 2, 3. I do 3 lines to show the 3 different rooms within that sublevel. And let's say there's 3 electrons that need to go in this sublevel. What I would do is put them in 3 separate orbitals. I'm not going to bunch them up together because those electrons want to spread out as much as possible within that sublevel. So this is the last slide, and you can see how we've mapped out all 7 energy levels with their sublevels and their orbitals. There's another way to represent this that really helps us understand what's going on, and it looks like this. This is the same thing as the last slide. You can see we have the first energy level right here. This would be the closest one to the nucleus. We have 1s. This is the 1 orbital within 1s. Notice, every s sublevel, look how many orbitals? 1, 1, 1, 1, 1. Because s sublevels have 1 orbital. Look at my p sublevels. They all have 3 orbitals. My d sublevels all have 5 orbitals. and my F sublevels have 7 orbitals. In each orbital, we can put 2 electrons. So 2 can go in 1s, 2 more can go in 2s, then we fill 2p, which can hold 6 because there's 3 orbitals, then 3s, 3p. You should notice that it doesn't always fill in order. How 4s is going to fill before 3d. We're starting at the bottom and we're moving up. This is called backfilling. We will talk more about this when we do more examples, but it's important to know that you don't just fill the first energy level, second, third, fourth, fifth, all the way up. Because of backfilling, some of these later energy levels start to overlap. This graphic here shows when you take all those Schrodinger equations and you kind of blend them together, putting all the orbitals around the nucleus. You can see an S sublevel is pretty simple. It's just a sphere. But when we start adding P sublevels and D sublevels, you can see that these clouds of probability around the nucleus start to really fill out. Remember, they're addresses, they're probable locations for electrons. And so you can see that when you get to an F sublevel, which has 7 orbitals, things can start to look pretty complicated because you have a lot of electrons to place around the nucleus. Here's another example of that orbital model. I know here in Unit 4 we've given you a lot of background information. It's because we really want you to understand where we're coming up with this electron configuration notation model. Why are we just placing things in random rooms? We're not. This is all based on science that was done in the early 1900s about how electrons behave with light, how electrons behave with energy, and how we place them in some kind of address or location around the nucleus. And honestly, what that can tell us about how those things are interacting with one another. And those things are important for things we see today, like the Large Hadron Collider over in Europe. Those things are based on science that Einstein and Schrodinger and Heisenberg did way back in the 1900s. And they're pertinent to our life now because they help us with things like technology and energy and what we understand about our physical world. So the next time we're together, we're definitely going to do some electron configurations. Hopefully you have a good background understanding of how we're coming up with those now that we've gone through 4.1 and 4.2.